G'day guys, welcome to the next lecture, and what we're going to look at today is the development of our universe. We're going to have two learning intentions today. We're first of all going to be able to hopefully describe two theories that have been used to explain how our universe developed, and we're going to look into one of those theories, the Big Bang Theory, and list and describe the evidence for that theory. Before we talk about what the Big Bang Theory is and some explanation of it, I just want to talk about what the idea is between what actually is a theory. Okay? In science, we've looked at two things. We've looked at laws and we've looked at theories. So Newton's law, you would remember from physics, is a widely tested and accepted description of how something behaves. So it's a description of a behaviour. That's what a law is. A theory is slightly different. A theory is an explanation of how something develops. Okay, so another theory is the theory of evolution, and that's the development of how animals and plants and organisms change over time. That's a theory. It's an explanation of how these things develop. It's not a description of how something behaves. That's the difference between a theory and a law. Okay, so this is an explanation, and it's a widely accepted explanation, but it's not the only explanation. Back in the 1940s, people were starting to look at the stars, and there was a lot of research going on. And during this time, there were actually two theories developed about the development of our universe. The first theory was called the steady state theory, and this is what a lot of people believed during the 1940s. And it suggested that the universe was infinite, which basically meant that it hasn't changed very much and it's always looked like it does now. For about 20 or 30 years, this is the explanation of the development of our universe that people actually believed. Over the same time, there was a scientist named Edwin Hubble who was doing some observation of distant galaxies. What he discovered was that the light from these galaxies was more red than it should be. His explanation for this was that the galaxies were moving away from the Earth. So this lengthened the light rays. So the universe, he took from this that the universe is expanding, and it must have been condensed at one point in time. But this wasn't enough to overrule the steady state theory. People still believed the steady state theory. It wasn't until 1965, when two astronomers were studying the Milky Way, that people started to believe more in the Big Bang Theory. While they were doing their research, there was some annoying background radiation, and it kept screwing up their results. Normally radiation would come from a source, so such as, back in that time, a radio tower or a TV tower which was near them. But they checked and there was no source for this radiation. They contacted a scientist named Bob Dick, who was actually part of the development of the Big Bang Theory, one of the scientists who was working on the Big Bang Theory. And one of the predictions was that there would be a background radiation, which would actually mean the temperature of the universe would be around about 3 degrees Kelvin. Kelvin we've looked at before, and it's a type of unit that we use to measure temperature, and 3 degrees Kelvin is minus 207 degrees Celsius. Very, very cold. But this would be the actual temperature of the universe, and all that radiation would be due to this 3 degrees Kelvin. With this explanation, people started to accept the steady state theory over the Big Bang Theory. And from about the 1970s, the Big Bang Theory became widely accepted in an attempt to explain how the universe developed. Okay, the key word here we're using is developed and not created. We're not talking about how the universe was created, we're talking about how it was developed. And we're saying that it was developed from what we call a singularity, which is basically a dot. No, sorry, that was a squiggle more than a dot, but a dot like that. A very, very dense dot. So the evidence for the Big Bang Theory. We're going to look into two things. The first one is the redshift of the galaxies, and that was what Edwin Hubble found. And then we're going to look very briefly at the cosmic background radiation, which is what the two astronomers found. Before we can understand the evidence of the redshift, we need to remember one thing. Visible light that we see in everyday life is a wave. Okay, it's a wave. And you can see the wave down here, and you can actually see how there's smaller waves, okay, narrower waves, what we call short wavelengths, and then there's longer waves, longer wavelengths down here. So blue colours have a shorter wavelength, red colours have a longer wavelength. Okay? Now, light is part of what we call the electromagnetic spectrum. Okay, let's see if I can get that down. And the electromagnetic spectrum incorporates a whole bunch of energies that we use in our everyday life. Okay, the electromagnetic spectrum, things like X-rays, things like UV rays, radio waves. Oops, there's an A in there. Radio waves, infrared. These are all part of the electromagnetic spectrum, and light is just one part of this. The other thing that we need to know about with the evidence for the red shift is this Doppler effect. Now, Doppler effect you may have heard of before, or you may have heard before, but not actually heard of the name. Think about hearing a siren when an ambulance goes past, or a fire engine goes past, or some police. As the car vehicle is approaching you, it sounds really high-pitched. And then as it's moving away from you, it sounds a little bit lower pitched. And what's happening is that these waves, because sound travels in waves just like light, these waves, when it's coming towards you, are being pushed together, which means they're narrowing. Okay, narrow wave means higher pitch. As the vehicle is moving away, it means that the wavelengths are getting longer. So that means a longer wavelength, which means lower pitch. Now, if we were to take out the sound and put the light in instead, this shorter wavelength would be the blue end. This longer wavelength would be the red end. So something that is moving towards you would be more blue. Something that is moving away from you would be more red. And that's exactly what Edwin Hubble found. Light that moves towards you, everything seems a little bit bluer. Light that moves away from you, and this is what he found with the galaxies, light from the galaxies seem to be more red than it should be. And that means that those galaxies are actually moving away. That's why he said that the universe was expanding, because the light was moving away and looking more red than it should be. So that's the evidence for the redshift. The other evidence is the cosmic background radiation. This can be sort of explained like a match. Imagine getting a match and you light it, just at the beginning of the universe. It's hot. Then what happens is you blow the match out. Now, that match initially will cool down over time. Okay, so what happens is that there's a little bit of radiation, heat radiation, left behind in this burnt match. Now, in a match, that's not very much, but we've got to remember we're dealing with the universe on a much, much, much larger scale. So there is a little bit of radiation, heat, if you would like, left. So that's what the cosmic background radiation was. Okay, it's that after the initial Big Bang, it cooled down, and what happened was there was some leftover radiation. Rightio, that was a quick lecture, and really what we looked at hopefully were the two theories, the steady state and the Big Bang theories that have been used to explain the development of our universe, and hopefully you can be able to list and describe the two different types of evidence for the Big Bang theory, the redshift of the galaxies and the cosmic background radiation. Hope you enjoyed that one, guys.